Welcome back. We want to continue talking about chapter 4, continue talking about chemical equations. We want to talk about how phases are represented in chemical equations. Okay, so we're going to stick with our same reaction. Propane and oxygen in the gas phase react to give carbon dioxide and water in the gas phase. And here is the chemical equation, the base chemical equation that we came up with in the last video. And so now what we want to do is we want to include the information about the phase of matter. And in order to do that, we use just single letters. They are lowercase letters. And we're going to put a lowercase letter in parentheses after each substance based on its phase of matter. So we use for gas, we use G. For liquid, we use L. We're not going crazy, just the first letter. And solid, we use S. You'll note they are all lower cases, G, L, and S. I will note real quick, when I'm going to handwrite these a decent amount. Liquids, I'm going to use a loopy L. I use a loopy L like that. You don't have to. The reason why I do that is just to denote that it's not a 1. I use loopy L's whenever I write, like chlorine symbol. I always use loopy L's. Later on, we'll talk about L's again. I always use loopy L's on my handwriting. You don't have to. But that is why I do that, just to distinguish it from a 1 or an I or something like that. For this particular reaction, we are told that everything is in the gas phase, right? Propane and oxygen in the gas phase, carbon dioxide and water in the gas phase. So we just add that G. We said that we used a lowercase g, and so we can see that every single substance gets a G. And they're all lowercase g's in parentheses right after the substance. Even though these are all gases, all of these symbols are exactly the same. Each substance needs one because each substance has its own phase that we want to be representing. All right, so our reaction description that we started with was propane and oxygen in the gas phase react to give carbon dioxide and water in the gas phase. We have completely represented that using this chemical equation. It is the complete description of what we were looking at, or what we were describing. It's much more condensed, right? It's much cleaner. You don't have to really read it out. Another thing that's really important is it's standardized, right? We talked about how you could identify, like verbs to know what reactants and products are. But people use a lot of varieties of language. Some people write chemical reactions, stylistically. The reactants will go first. We got carbon dioxide and water from reacting propane and oxygen. And so we just want to be consistent, and chemical equations give us a nice, clean, systematic way to represent reactions. Exactly what the reactants are, what the formulas are, what the products are. You don't need to worry about systematic names, common names. Just have the explicit formula there. Along those lines, formulas and naming, like we talked about previously, are still here, right? We still want to be able to use those ideas, use those concepts, and work our way through ideas, understanding when we're talking about different substances, what they are. Let's take a look at some examples now of writing chemical equations. So write the chemical equation for the melting of ice. And so whenever we see this, whenever we see that we want a chemical equation, that's what we're after, right? What does this problem want as a chemical equation? We know that a chemical equation always has two parts, reactants and products. So good place to start is, what are the reactants? Well, sometimes they're given to us, like in the sample problem they were, but in this case, we need to figure it out based off of the process that we're looking at. We're looking at melting of ice. So we know that means that we're starting with ice. And ice is solid water, right? Ice is not the name of a substance. Ice is the name of a phase of water. So that's solid water. What are the products? Every chemical equation has that. So again, melting of ice, we know when you melt, you go from solid to liquid, so we make liquid water. So solid water to liquid water, our chemical equation is going to look like this. H2O solid becomes H2O liquid. You will note that with this chemical equation, without the phases, this would be nonsensical. It'd be water becoming water. That's not a change. Okay. We see here that with this representation, with the phases, that allows us to completely capture what's actually going on. That solid is becoming liquid. You can also note this is a physical change. This is melting of ice. That's a phase change. And this equation that we've written really shows that. It is water becoming water. The only thing that changes is the phase, which is really clearly demonstrated. And we can also see that the substance really isn't changing. It's still water as a solid into water as a liquid. When we're dealing with using these sorts of phases, they're going to be really important, based on what we have. And in general, when we're dealing with phases, sometimes we'll learn places where we can figure them out. But a lot of times, you just want to use the phase that's specified in the description. We started with this burning of propane, and you may have noticed that we produced liquid water as a gas. Under room kind of conditions, ambient conditions, water is a liquid. But here, water is a gas producing this process because this is burning propane, which produces fire. So you're producing fire. That's why, and the water is hot. So the water is produced in the gas phase. So that's why it was a gas. Again, over on the ice melting, we were told we started with ice. So don't overthink it. Don't look up what water tends to be. You were told it was melting ice. So you know that is solid into liquid. You can't always look up if you're dealing with ambient conditions. You can't always look up what the phase of matter is, though. We talked in chapter 3 about the importance of dissolving substances in water. And so aqueous was our term for anything that was dissolved in water, where we do a lot of our chemistry. And we have a special format to describe this. We use a phase as AQ in parentheses. And we use this in the exact same way that we would use our solid. So dissolving sugar, for example, you start with solid sugar and it becomes aqueous sugar, or AQ sugar. And so that AQ means aqueous. Whenever we see AQ, that means dissolved in water. Again, it's the first letters. It's the first couple letters of the word of the phase, right? AQ. But you'll note that it's 2 letters. That's because it is dissolved. It is a salt. You're talking about a solution, not a pure phase. Pure phases get single letters. So this is a 2 letters because it's a solution. But we do want a separate distinction. We wouldn't call it L. We wouldn't call it a liquid because this is not liquid sucrose down in here. It is dissolved in water, so it gets a special designation as aqueous. So let's write the chemical equation for the dissolution of sucrose, C12H22O11. That was what we showed the pictures of on the last slide. So that was a process. Again, we want a chemical equation. So we're always going to start by asking what are the reactants. And we can see we're dissolving sucrose. So that means we're starting with solid sucrose. We also know that water is involved, right? We're dissolving sucrose in water, so water is involved in this process. Well, what are the products? Well, we get dissolved sucrose, which is aqueous. Is there also water? There's still water around, right? There's still liquid water that's dissolving it. There's still water that's present. And so we could write it out to look something like this. We can see the changes. We have the solid sucrose becoming the aqueous sucrose. But then if we look, we can see we have water as a liquid showing up on the reactant side and the product side. That's no good. We never want to have any substance show up in both places. We have liquid water, we still have liquid water. That's not a change. We are looking to use chemical equations to describe changes. So yes, water is present. Water is an important part of this. But it is not actually what's changing. What's changing is the sucrose, the C12H22O11. It's going from being solid to being dissolved, which we describe using the AQ as the phase. We never want to have any substance show up as both a reactant and a product in any chemical equation. If you write a chemical equation and you have the same product, or the same substance as both a reactant and a product, that is a problem. That is not a correct chemical equation. So there are ways to convey this information, though. That water is involved in dissolving, and what we do is we put it over the arrow in between reactants and products. So the more correct description of dissolving sucrose is this top one. We can see we have solid becoming aqueous, which is fine. And then if we want to specify that there is water involved, we can put it over the arrow. We should note that is entirely optional. You don't have to put it there, because when that final phase is AQ, that inherently implies that it is dissolved in water. There's only one way to get that, and there's only one way to become aqueous, and you have to be dissolving it in water. So it would necessarily be implied, but you can, kind of give some extra information, help out the reader. You can also give information about how to do a chemical reaction. For example, delta, that's just a triangle, indicates heating. So if you take ammonium chloride and you heat it up, you will get ammonia and HCl. So you would produce those products if you heated up ammonium chloride. You can also be more helpful and give specific temperatures. So this is called formic acid. If you heat it up to 160 degrees, you get CO2 and hydrogen, right? So you can get carbon dioxide and hydrogen if you heat it up to 160. So you can kind of see that if you think about like chemical reactions as kind of processes, or like a recipe, your reactants are your ingredients, and then over the line you put like cooking instructions, and then you get the products on the other side. But again, those are entirely optional. You won't see them a lot. You won't see them as much because chemists are pretty lazy, but you certainly can use that, and that would be the appropriate place to put that information. You wouldn't want to put it as a reactant or a product.